Hey guys, my name is Brendon. I'm going to be your math tutor for this video. In this video, we're going to go ahead and get into the integral test, which is a series test that we can use to check for convergence or divergence. So yeah, let's go ahead and get into it. Alright, so let's go ahead and get into the integral test. So we're going to start with a series from n is equal to 1 to infinity of a of n, and a of n is just a function of n. Okay, and so we're going to say that that function of n is similar to a function of x, and then the integral test says that if we can show that f of x is positive, decreasing, and continuous, and if we can show that the integral from 1 to infinity of f of x dx, if we can show that that integral either converges or diverges, then that tells us that the series also converges or diverges. So let's go ahead and do an example and see what this looks like. So if we start out with the series from n is equal to 1 to infinity of n over n squared plus 1. Okay, so let's go ahead and identify our piece. So we have f of n is equal to n over n squared plus 1. And then that's going to be similar to the function f of x is equal to x over x squared plus 1. Okay, so now let's look back up at our three stipulations to the integral test. First, we have to show that it's positive on the interval. Then we have to show that it's decreasing on the interval and it's continuous on the interval. Okay, so let's go ahead and identify what is our interval. So our interval is going to be shown up in the series. So if we're going from 1 to infinity, and in this case it's 1 to infinity as well. So let's go ahead and check off to see if it's positive. So if we look at our function x over x squared plus 1, there's no negatives in this function. And if our integral or our interval is going from 1 to infinity, all positive numbers, we're only plugging in positive numbers to this function, which also has no negative numbers. So that tells us that this function is always going to be positive. Okay, so let's go ahead and we can check that one off. So we've shown that this is always positive. Now we need to check to see if it's always decreasing. And so the way that we can check that is if one way we can do it is we can plug in a couple values to start out, or if we just look at this function. So our denominator is x squared plus 1. This is always going to be bigger than our numerator. So if our numerator is just x and our denominator has an x squared plus some extra to it, we know that our denominator is going to be getting bigger and bigger and bigger faster than our numerator is. So then that tells us that our function is decreasing. Okay, so then now we need to check to see if it's continuous. And so if we look at our denominator, we want to show that this doesn't equal 0, right? And so let's write this one out. So if I want to say that x squared, we're going to try to find plus 1 if this is ever equal to 0. So then I'm going to subtract 1, so we get x squared is equal to negative 1. And we know that when we're plugging in a positive number and squaring it, we're never going to get a negative number. So on this interval, our function doesn't have a denominator that's ever going to be equal to 0, meaning that it's continuous because the numerator of our function is also continuous. Okay, so we've checked off all three of the stipulations that we need to be able to do the integral test. So now we can actually go ahead and do it. So let's go ahead and plug in our integrals. So this is going to be the integral from 1 to infinity of f of x, which is going to be x over x squared plus 1 dx. Okay, so this is an indefinite integral, or sorry, an improper integral. So if you're unfamiliar with solving an improper integral, I would highly recommend going back to that section and reviewing that section. But we're going to go ahead and solve this. So the way to solve an improper integral is we're gonna substitute this infinity in the bounds of the integral for a variable, and we're going to take the limit as that variable goes to infinity. So this is going to look like the limit is, I'm going to use t. As t approaches infinity of the integral from 1 to t of x over x squared plus 1 dx. Okay, so now we just want to go ahead and solve this integral like normal. And then, so the way that we're going to do that, this one, it looks like it's going to be a u substitution. So we're going to substitute the bottom for our u. So it's going to be x squared plus 1. So then du is going to be 2x dx. Okay, and the way I like to do these is I'm going to go ahead and solve for my dx. So dx is going to end up being du over 2x. Okay, so let's go ahead and plug everything back in. So this is going to be the limit as t approaches infinity. And I'm not going to write the bounds on it because I'm going to plug the bounds back in when I substitute back in for x. Otherwise, you have to substitute your bounds into your u equation and then solve with u bounds. So we're going to end up with x over, so u, this was our substituted piece, and then dx we solved for over here, which is du over 2x. Okay, so we're going to go ahead and cancel out the x's, and I can pull this 2 that's in the denominator, I can pull it out as a 1/2. So this is going to be the limit as t approaches infinity of the integral of 1/2 times the integral of du over u. Okay, and so then this integral is just going to come out to be the natural log of u. So this is going to be the limit as t approaches infinity of 1/2 times ln of u, and then let's go ahead and plug in our substituted u piece. So this can be the limit as t approaches infinity of 1/2 times the natural log of x squared plus 1. Okay, and so now what we can do is we can evaluate it at our bounds, which were 1 to t. Okay, so now let's go ahead and go up here and plug in our bounds. So this is going to be the limit as t approaches infinity of 1/2 times, let's see, it's going to end up being the natural log of, so x, I'm going to plug in my t, so we get t squared plus 1 minus the natural log of, looks like I'm going to end up with 1 squared plus 1, which is just going to be 2. Okay. All right, so now let's go ahead and what we can do is we can plug in our limit. So then this is going to be 1/2 times the ln of infinity plus 1, or infinity squared, sorry, plus 1 minus the ln of 2. Okay, and so we know that as the natural log, as our argument of our natural log goes to infinity, the natural log also goes to infinity. And so if I'm subtracting off this little constant piece, since this is getting bigger and bigger and bigger, this little constant piece doesn't matter, and we're still going to be going to infinity. So then that tells us that this integral diverges towards infinity. And so since we know that by the integral test, our integral diverges towards infinity, that tells us that our series is also going to diverge. Okay, so that's how you show how a series diverges using the integral test. And so just remember the 3 stipulations. You have to show that the function is positive, you have to show that it's decreasing, and you have to show that it's continuous. And then you can go ahead and solve the improper integral for your argument of the series. And then if that improper integral diverges, your series also diverges. If that improper integral converges, then your series converges. So in the next video, I'm going to go ahead and do a series that is going to converge. All right, thanks for watching.